Okay, good morning, everybody. So I guess I'm going to kick off the day today. I'm going to make you a little bit hungry. I'm pretty sure we've all seen menus like these. They're pretty boring. You have to go through them. Look for a very specific food item, for a very specific extra, something that you really want. Maybe something that you don't know that you want. Well, maybe you want to order from an application that is basically fast. It's sleek, it's versatile, it's efficient, it's tailored to your needs, and most importantly, it's personalized. Well, maybe you just want a friend that you could text, you could talk to, ask for recommendations, make them do your order. Well, we created your new friend, Yum. Yum is a personalized food ordering chatbot presented to you by Youssef Agiza, Mariam Elsaqa, Seif Sallam, Nagham Mekky, Dalia Elnagar, and yours truly, Kirolos Mikhail. We were able to create this masterpiece under the supervision of Dr. Nouri Sakr, Dr. Hossam Sharara, and in collaboration with engineer Mina from Google. So what are we going to talk about today? Today, we're mainly going to cover the technological aspect of our project. We're going to show you how the app is going to work, give you the business plan for this amazing masterpiece, and finally talk about the future of our application. So let's start off with the technology.
As you see over here, this is architecture of a diagram architecture of the application we have built so far, including all of the components we have developed throughout our thesis project. First, we have the front-end client application, which interacts directly with the user and take the user input to send to the back-end. Then we have the natural language understanding unit, which includes an intent classifier, which understands what a user wants to do, a binary classifier, which decides whether a user wants to confirm an order or cancel it, and of course, a named entry recognition model in order to extract important information from the user input. We also have a recommendation engine in order to give user recommendation, and of course, a large language model to communicate with the user. As for database, we have two databases, one for orders and one for restaurants, and all of this is integrated together in our backend.
Well, we've all heard the term machine learning model, AI. All these terms are fun, but how do you create your machine learning model? You need to train a model to be able to do your task, the task that you want it to do. So how do we train 5 machine learning models? By getting a lot of data. We're able to scrape 90 gigabytes worth of data from restaurants, from menu items, from different categories, different cuisines, a lot of different data sets that we then use to generate more data to be tailored for each and every model that we used.
Now let's talk about the first model in our system, the intent classifier. This model basically tries to understand what the user wants, the intention or the intent of the user. Our model has learned 7 different intents, such as build order and inquiry. Let's say that the user says, I want to order a cheeseburger and fries. The model then understands that as the user wants to build an order. So how did we do that exactly? Originally, we used a pre-trained BERT model. However, it did not satisfy our task, so we trained it ourselves with our own data.
In order to extract important information from the user input, we needed a named entry recognition model. This model extracts information such as restaurants and food items, as well as the action that needs to be done to this food item, whether to add it to the order, remove it, or modify it. So how did we build this component? We decided to fine-tune this BERT model. However, we needed a data set for our use case. We needed sentences of users making or modifying orders, as well as the entities that each word belonged to. Over here, you can see the entities we decided we need for our model, and since there is no such data exists online, we decided to create our own data set with the help of the data we have already scraped, as well as ChatGPT. After some prompt engineering, we were able to create several prompts for different order actions and sent them through ChatGPT APIs. And these prompts were also integrated with orders from the data set we have scraped. After creating a data set of 72,000 samples, we were able to fine-tune our model and got back these promising results with accuracy about 95%.
And now for the recommendation engine. For the recommendation engine, we have decided to implement a hybrid model that consists of 3 different models. We have made this decision to have a better recommendation engine and a better personalized experience. The three models that we have decided are content-based filtering, collaborative filtering, and knowledge-based filtering. First of all, is the content-based filtering. Content-based filtering is a recommendation that is generated based on the similarities between restaurant features. We decided to implement this specific model because it does not rely on user history, and it's very hard to generate human pattern-like data, so we had to rely on the data that we have scraped already. We implemented this model by first of all, pre-processing our data, and then we analyzed our data and extracted the features, and then we used these features to compute the cosine similarity that grouped similar restaurants together, and then we sort them based on the mean rating, and then we just select the top restaurants. The second method that we had implemented is a collaborative filtering. Collaborative filtering is also generating recommendation, but this time it's based on the similarities between the user history. The problem that I have just mentioned about that we cannot generate user history. So we had actually implemented this model, but we couldn't integrate it, unfortunately. So this model basically detects the hidden patterns between the user characteristics. And then we implemented this model by using the same pre-processing function that we had used already for the content-based filtering. And then we feed this characteristics and these features to a KNN network, that just get the similar restaurants together and give us the output. And then finally, we have the knowledge-based filtration, and knowledge-based filtration is generating recommendation based on preset user preferences. And we have decided to use this specific model because to solve the cold start problem. What is a cold start problem? Cold start problem is basically when we don't have enough data for a user that is asking for recommendation for the first time. So we ask him for to enter his preferences through this interface, and then we use his input to generate recommendations for him. We implement this model using two methods: database query for any ordinary data, and then we use R3 index for spatial data specifically.
Okay, so what is the binary classifier that we have in our system? The binary classifier that we have is a machine learning model that uses the user text and classifies it to be either positive or negative. But why do we need such a model in our system? Well, we use it sometimes to know if the user wants to confirm or deny the request or the information that we were given and processed in specific situations. For example, if we have a place order intent and we want to place the order, the user needs to confirm if he actually wants to place this exact order or he wants to deny it. This is why we chose it. How did we do that? Well, we utilized a large language model that was optimized for a sentiment analysis task. And the sentiment analysis task was very much efficient and enough to get our use case into work. Oh, what are these? These are llamas. You're looking at something in the laptop. It's LLMs. All right, I guess we're going to talk about LLMs at this point. So what are LLMs? LLMs are basically large language models. So far, we've only talked about the NLU part. NLU is natural language understanding. And it's basically just understanding what the user wants to convey by the message he's saying and what he wants to do with our system. But there must be something else in that formula that tells the user what these information is, that drives the conversation forward, and we know what else should happen. And that something is a large language model. So what is a large language model? A large language model is a machine learning model that understands the user sentences and the human language and is able to interact with it. Why do we need such model? Because we want to have a human-like conversation between the AI and the user. So how did we do that? We did it by pre-training, fine-tuning a pre-trained model already trained on conversational tasks and is able to drive conversations between the user. And we trained it further on our own custom data set. Okay, so how did we actually do that? We tested and chose between several pre-trained models and was able to land on the Llama family created by Meta, or previously known as Facebook. And we found LMSys, another organization interested in AI with large language models, created Vicona. Vicona, if you don't know, it's also part of the Llama family. It's based on Llama 2. It's a 13 billion parameter model and was a perfect fit for our use case from the get-go. However, we wanted to create a new data set that is recognizing the same intents the intent classifier recognizes, because we want to bridge the gap between the two models. And we also made sure that the data set included several examples and several samples just to let the model understand the instructions and how to respond to it, understand the set of rules, and be able to generally understand the task. Okay, so at this point, what can Yum do? Yum can consider the user input, system instructions, system messages, and answer accordingly. In fact, he can answer all the questions regarding the task, at least all valid ones. Any invalid or unsupported questions will be recognized and will be regarded to Yum as unsupported. And he will be able to tell you, the user, that he's doing X, Y, and Z, and he cannot do that. You might be asking what type of unsupported question he can ask. Anything that is outside the food ordering scheme. Something like asking about the weather. Okay, why don't we just build our own model? Why not use the famous ChatGPT? Well, that's a very good question to ask. However, ChatGPT is a very large and generic model, and research proved that building a model from the ground up is a very bad and useless and pointless idea, because it will never give you the same output, it will never give you the same efficiency, it will cost a lot more, and it will be not power efficient. And fine-tuning a smaller model would be the way to go. It is the best solution for efficiency, reliability, and having a lower power consumption, thus lowering the carbon footprint in the world. So is this an easy ride? Was this not very hard? Does this seem very simple and straightforward? Definitely not. The development challenges were many. It was an extremely challenging task. It took over 25 iterations with different models, different model sizes, data set creation, data set cleansing, over 120 hours of prompt engineering, over 30 days of 30 full days of training, plus 2 power cuts. And with that, Yum was born.
Okay, so let's wrap up what we have so far. So far, we have 5 different models. 4 of these models are models that we trained ourselves, and only one that we took as it is to use directly. Let's move on to our backend engine. It's the engine that's empowering all the models that we have discussed so far. And we can discuss the backend engine from 2 different perspectives. First is the design perspective. So from the design perspective, our design is based on having modular components. And what we mean by modular here is that each and every component is separate, independent, and it does not affect the other components. To achieve that, we have utilized containerization and Docker technology in order to have each component containerized and self-contained on its own. In turn, we achieved having a scalable system. What do we mean by scalable system here is that whenever we need to increase any of our components, we can easily spin up more models. We can increase the number of models that we have so far easily without affecting the system to utilize our models to affect or being able to handle higher scale or larger scale. Finally, all of these together can help us have what we call a plug-and-play design. So what we mean by plug-and-play here is the fact that each and every component is completely independent from the other components. We can easily remove and add other components to our project. We can remove models that we don't need. We can add other models in the future expansions to our system without affecting the workflow of our system. So that gives us the flexibility and scalability to grow our project whenever we need and how we need it according to our use case. Second, we can discuss it from the implementation perspective. We have 3 main implementation perspectives that we need to discuss. First is orchestrating the model. Our backend is responsible for orchestrating all the models that we have discussed so far in order to have the input and the output flow correctly at the right sequence from our project. For example, a typical user message will be given to the intent classifier to determine the right intent of the user. And based on this intent, we will go in the right flow in our backend in order to achieve the user's request. However, to achieve the request, we also need to implement our own custom algorithms. We need to implement algorithms to empower our logic to further comprehend the input of the user and be able to achieve and fulfill the request that the users need. So for example, when the user asks for building an order, we need to figure out the right entities from the named entity recognition and use that to find the data in our database in order to build their order. However, as I just mentioned, we need to find the data in our database. And to do that, we needed to do full text search. What do we mean here is that all the text that we have so far, all the input that we have so far is actually text-based. The user is only giving us text. And we need to do search in our data in order to find the closest results. And based on these results, and based on the confidence in our results, we can start to navigate the user either by fulfilling the request directly or navigate them and guide them to take the right actions. So for example, if they are searching for an item or asking for an item that we don't have in our database, we need to tell them that we don't have them and hopefully give them an alternative to use.
Okay, and now let's see Yum. That is actually, it is implemented using X for React Native. And we can see here that the user is starting a new chat by greetings, and then he is asking for recommendation. So the NER will see that it's an inquiry, and the IC will determine that pizza is a food. Our user is still asking for a specific food item that he doesn't know what he wants to order. So the NER will actually still see that it's an inquiry, and then IC will see Venice as a restaurant and pizza as a food. Then our user will start building his order by placing pizza as his food item, buffalo spicy pizza as his item that he wants to order. And then he's still building the order, and Yom is asking him about his preferences as a size. So NER will still build the order, and large will be determined as a size. And then our user wants fries with his order. So fries is the food, and NER is still recognizing it as building order. Then we can see that our user can spell bytes, unfortunately, but still LLM can recognize it as the wrong, the right thing to, that in our database. So our user is undecisive. He doesn't want fries anymore. So NER is still building the order, and fries is the food, but this time we are removing it from the order. And then finally, he knows now what he wants to order. So we are finally placing our order, and then we will reiterate the order for him, and then he can go and see the details of his order down to the tiniest detail.
So now that we have covered the technicalities of the application and that we've seen a quick demonstration, let's get down to business. So you might be asking, why would I use Yum? Why would I use your chatbot? For starters, simply because we're different. With us, you'd say no more to endless scrolling, high service costs, confusing menus, unsatisfying outcomes, and in general, with us, you have an overall better user experience. So to summarize our positioning our strategic position in the marketplace, we do a quick SWOT analysis. The SWOT analysis consists of 4 components: strengths, weaknesses, opportunities, and threats. Starting off with our strengths, Yum offers a personalized and human-like user experience, and our application is very, very scalable, so it would grow with the market. Our main weakness, however, is the lack of data availability. For our opportunities, however, we could collaborate with the restaurants, getting exclusive offers and deals getting more users to use our application, and integrating with emerging technologies, with newer LLMs, so on and so forth. And finally, our threats would be that other larger companies have a lot more user data that we have, so they can also create a product similar to ours. And in general, the food industry is a very, very competitive market, so it would be hard to enter.
Okay, so let's stop here for a second. Like any great business, there's always space to improve and grow. That's why we have future plans to improve our business. First off, starting by improving our search functionality. As I mentioned earlier, all of our information is based on being able to search the input given by the user and searching it from the data in the database. Accordingly, we implemented one of the searching mechanisms that we have. However, there's always space to improve that searching algorithm to be able to find better results for the users. Second is integrating the remaining recommendation systems. As we mentioned, the recommendation is the part that's personalizing our experience, and it's an important part of our project. We have only integrated so far one of the 3 models that we have, so we are going to implement it to integrate the 2 other components. Third is improving our NLU part. So all of our project, all of the components of our project depend on primarily being able to understand what the user are giving. So there are more components, there are more models that we can actually integrate in our system. For example, dependency parser model, to be able to understand the user input better and improve our project. Finally, is having a better and proper data set. All of our project, all the models that we have primarily depend on having data that can empower our project. So having better data, having more proper data that we can gather by releasing our application is an important step for us to be able to improve our models. Okay, so to sum up our journey so far, this is a journey that started actually 1 year ago. All of our team has been working for approximately 1 year endlessly and putting a lot of effort, pursuing to have the best project that we could have achieved. For us, we see Yum as not as just a chatbot, but actually a trustworthy companion that is meticulously designed to improve and help the users to have the best user experience. Of course, there's no doubt there is space to improve. There's no doubt that Yum can become better. However, we see this as endless potential that Yum have, that we think by giving more improvement, having more refinement, we can give the best user experience that we can achieve. Thank you.